Welcome back, my dear students. I know. Exams are just around the corner, and everyone's feeling that pressure, right? Especially with this chapter, rotational motion. So many of you have told me, sir, this chapter's tricky. But listen, don't you worry one bit. Together, we are going to break it all down and make it super, super simple. Bilkul tension nahi lena. Okay, so you've all seen those incredible dancers on Instagram or YouTube Shorts, haven't you? They start spinning slowly, pull their arms in, and suddenly, whoosh, they're spinning like a top. How in the world do they do that? Or think about a simple seesaw in the park. How does it balance so perfectly, even with two different sized people on it? Well, the secret, my friends, is all in this chapter. Stick with me, and I promise by the end of this, you'll know the secret too. All right, let's just jump right in, shall we? So before we can master all that spinning stuff, we've got to get the basics down. You see, any object we're going to talk about, what we physicists call a rigid body, can really only move in two main ways. Now, have a look here. This is really the core difference. On the left, you see pure translation. Just think of a book sliding across a table. Every single little piece of that book moves with the exact same speed. Simple, right? But now look on the right, we've got rolling. Imagine a cricket ball rolling on the pitch. It's moving forward, that's the translation part, but it's also spinning. And this is the cool part. It means the tiny bit of the ball at the very top is actually moving faster than the bit at the bottom. So it's a mix of both motions. So you're going to hear me use this term rigid body a lot, but what is it? It's super simple, really. It's just any object that doesn't bend or change its shape. The distance between any 2 points inside it, it stays completely fixed. Now, okay, in the real world, nothing is perfectly rigid. But for our physics problems, things like a cricket bat, a wheel, or a steel beam, these are our perfect examples. This rigid body is basically the hero of our story today. Okay, now for the cool part. Every single object has this, well, it's like a special, almost magical point. It's this one single point where it feels like the entire mass of the object is packed together. And this, Bachelog, is the absolute key to understanding balance and motion. We call it the center of mass. In this picture, it shows the concept perfectly. Think about it. If you have something symmetric, like a uniform ruler or this rod, where would you try to balance it on your finger? Right in the middle, of course. That balancing point is its center of mass. So for symmetrical things, it's always at their geometric center. Easy peasy. But what about objects that aren't perfectly symmetric? Well, for that, we need a formula. Now hold on, don't get scared by the math. Think of it this way. It's just like calculating your final marks in school. You take the marks in each subject, multiply by its weightage, add them all up, and then divide by the total weightage, right? We do the exact same thing here, but with mass and position. So the main idea to remember is that the center of mass is just the mass-weighted average position of all the particles. Okay, so we all know what makes an object move in a straight line, right? A force. You push it, it moves. But what makes an object turn or spin? For that, we need a special kind of oomph. Let's find out what that is. Just think about opening a door. We do it every day. Now, if you try to push the door open right next to the hinges, you have to push really hard, don't you? It's tough. But if you push on the handle, which is far away from the hinges, it swings open so easily. You could be using the same amount of force, but the effect is totally different. This tells us something super important. For rotation, it's not just about how much force you apply, but also where you apply it. And this turning effect of a force, it has a special name. It's called torque. Simple as that. Just like force causes straight line motion, torque causes rotational motion. The formula you see? Torque, represented by that Greek letter tau, is R cross F. Now, R is just the distance from the pivot point, like the hinge of the door, and F is the force you apply. So the further you are from the pivot, meaning a larger R, the more torque you get for the very same force. And that, my friends, is exactly why the door handle works so well. All right, now we're getting to the really cool part. Remember that spinning dancer from the beginning? Well, this next concept is the master key to unlocking her secret. It's called angular momentum. You guys all remember linear momentum, right? That old friend, P equals m times v. It's basically the amount of motion an object has in a straight line. We'll say hello to its rotational cousin, angular momentum, L. It's the quantity of rotational motion. And here's the beautiful part. Just like linear momentum only changes if an external force acts on it, angular momentum only changes if an external torque acts on it. See that perfect symmetry? That's what makes physics so elegant. And this brings us to one of the most powerful, most important laws in all of physics. And listen carefully, this is a very important one for your exams. It's the law of conservation of angular momentum. And what does it say? It's actually very simple. If there is no external twisting force, no external torque acting on a spinning system, then its total amount of spin, its angular momentum, will not change. It stays constant. That's it.
So let's solve the mystery of the dancer. When she's spinning with her arms stretched out, the mass of her arms is at a large distance, a large R, from the center of her body. Then she pulls her arms in. What happens? She reduces that R. But remember the law we just learned? Since there's no one pushing or pulling her, no external torque, her total angular momentum, L time, has to stay the same. It must be conserved. So if L has to stay constant and her R gets smaller, something else has to get bigger to compensate. And what's that something? Her speed of rotation. And that's why she spins faster. Simple, Henna.
Okay, theory is all well and good, but we all know that marks come from solving questions, right? So let's tackle a typical exam question together. This will show you exactly how to apply these concepts and nail those full marks.
All right, here's our question, and it's based directly on a solved example from your textbook. We've got 3 particles with different masses, 100 grams, 150 grams, and 200 grams. They're placed at the corners of an equilateral triangle with a side length of 0.5 meters. Our job? Find the center of mass of this whole system.
So what is the very first thing you do in a problem like this? Always, and I mean always, set up your coordinate axes. Trust me, it makes your life so much easier. So let's do what the slide says and place the 100-gram mass right at the origin. That makes its coordinates easy, 0, 0. Now, since the side of the triangle is 0.5 meters, the 150-gram mass will be on the x-axis at 0.50. And with a little bit of simple geometry, we can figure out the coordinates for that 200-gram mass at the top. Okay, first up, let's find the x-coordinate of the center of mass. We're going to use our weighted average formula. So, step 1, write down the formula. Now for step 2, we just plug in the values. Mass 1 times its x-coordinate, plus mass 2 times its x-coordinate, plus mass 3 times its x-coordinate, all of that divided by the total mass. Do a little bit of simple calculation in step 3, and boom, we get our x-coordinate, 5 by 18 meters. And now for the y-coordinate. Guess what? We do the exact same thing. Same formula, but this time we use the y values. Now just notice that the first 2 masses are sitting on the x-axis, so their y-coordinate is simply 0, which makes our calculation easier. We plug everything in, do the math, and we get the y-coordinate as √3 by 9 meters. So our final answer, the location of our center of mass, is at the point 5 by 18, √39. See, when you break it down into simple steps, it's not so difficult at all. Wow, we have covered a lot of ground. So to make sure all of this sticks in your head, I've made a super quick summary for you. This is perfect. You can even take a screenshot of the next slide for your last-minute revision right before the exam. And here it is, the entire chapter on one single slide. Let's just boil it down. Center of mass tells you where an object balances. Torque tells you how to make it turn. Angular momentum tells you how much spin it has. And the golden rule, the conservation law, tells you that the spin won't change unless an outside torque messes with it. If you can just remember these 4 key ideas, believe me, you have mastered the heart of this chapter. So there you have it, rotational motion made easy. Just for you. You've understood the concepts. You've even solved a tricky problem. You are ready. You've absolutely got this. Now just go and practice a few more questions on your own. Tension nahi lena bachcha log. Go and rock your exams. All the very, very best.